So yeah, it's been a while since I uploaded the last video. Anyway, so I recall that last time I talked about what are projective modules. So in our module, M is projective if this covariant functor is exact, right? So this was our definition of a projective module. So in this video I will talk about these projective modules in details. So yeah, so for example, let's see some examples. Z is a projective abelian group. That is, it's a projective Z module. Yeah. And not only Z, any free abelian group on Z of say finite rank, say R, for all R. Right? And also, let's see. So we'll see why these are projective modules. But for now, let's just give some examples. Also, say you can say whether Q is projective as Z module or not. So yeah, these are the some things like these are the some questions that you should think of. Anyway, so let's see some equivalent criteria for a module to be projective. So projective module. So we'll set this is the usual definition, that is this home functor is exact. This was our number one, following our equivalent. Number two is uh, so what does it imply? It implies that whenever you have a surjective map, you get a map from home A to home B, right? So home MA to home MB. So what you do, you take any field, you put it as it is from it into A and just recompose it with A. We will get a map from M to B. So this is exact. Or so what does it imply? It implies that given a surjective map, here map means homomorphism, of course. So given a onto map from A to B and given any psi from M to B, there exists some phi from M to A such that psi is if compose phi. That is same as saying that this is exact, right? So first two things are equivalent. That is obvious from the definition. Now let's see the third one. It says that uh, any projective module can be written as a direct summand of free module. This means that is if P is projective or say M is projective, then there exists some free module F such that F is M directs some other module CK, right? So and number four is any short exact sequence ending at P or ending at M splits. That is, if you have any short exact sequence of this form, then you get like this. So let's see. The first two things are, of course, obvious. So I'm not going to comment it. Anyway, for let's see how to tackle number three and number four. So for that, let's see. Uh, suppose let's do it for. So you have this to this to this. So here let's call this map G, let's call this map F. So F is an onto map. So if M is projective, then for this onto map, and you have, let me change the color. So you already have this map from M to M, that is the identity map, right? So by definition of projective, you get some map from M to B, let's say, let's call it F bar, such that this diagram is convoluted, right? That is from the definition. So if you assume one or two equivalents, so you get a section that is a map in other direction from M to B F prime, such that their composition. So what is the composition? It is you start from M. So yeah, so this is identity, right? So that is equivalent to saying that this sequence is split. So yeah, so one implies four. And now let's see how uh, say 4 implies 3. That is easy because uh, so so we have say if you have any module, you can always write it as a quotient of a free module, right? That is because because of the universal property of free module. So given any module M, you get a surjective map from some free module F to M, right? This is the obvious surjection, and then you can write it as if you write K as the kernel of this map, so that is isomorphic to M, right? And so readily we get a short exact sequence from 0 to K. So this is the inclusion from K to F, and you have the projection, right? And because M is projective, so you get that F is a direct sum of M and K. That is what 3 says. So we get uh, 1 implies 2, then or 1 or 2 an equivalent. So let's just keep them as a single one. And we have seen 1 implies 4, 4 implies 3, and 1 and 2 are same. So it's enough if we show that say 2 implies 3, right? Or maybe 3 implies 2, or 4 implies 2, or 4 implies 1, anything. So let's see. So let's see which one is easier to prove. So without suppose let's do this one. So let's start with a surjective map F from A to B, and a map psi from M to B. We need a map from mm, M to F. We says that this is commutative. And for that, uh, so let's see. So we need a map from M to A, and from 3 we have uh, F is, so there is some pre-module F says that F is a direct sum of M and K. So you can push M inside F, right? Because you can identify M as a submodule of F. So now what you can do, so any element of F you can project it onto its first component, that is M, right? If you identify F as the M direct sum K. So you have a map from uh, M to, oh sorry, F to M, and that is you have a map from, let's call this map I. So you have a map from F to B, that is the composition of psi and so what it does now, somehow maybe if we can show that there is such a map, uh, say phi bar from F to A, I think things are uh, easy to show after that. So let's see how to do it. So you have a map from uh, F to B, and let's just define a map from F to A. And that is pretty obvious because so take any element X from F, and you can uh, map it to B via this Shai composite. And remember, F is surjective, right? So this will have some pre-image, some small. So we define this map from F to A as this X going to this small. So we have a map from F to A, right? And now to check well defined, it's like it could be the case that there exists more than one pre-image of an element under F. So in that case, if say suppose you have another element f of A shall compose Ix and f of say, B is also this. So you get that uh, A minus B is inside the kernel of F, right? And so yeah, but then I think so then you get A minus B will go to 0 under it. And what we need to show is that so basically if there exists another preimage, so that will not matter. That is what we needed to show. And for that, let's see. So A minus B is in inside the kernel. And so X will so under F A minus B will go to say 0, right? And then what we can do is maybe say so yeah. So we have psi I of X is basically f of A, right? And then yeah, okay. So now what we can do is, or maybe we can uh, make it like slightly different. Yeah. So what we have, A to B to 0. This is an exact sequence. We have a map from M to B. We have this, right? And so if you have any element X, we can push it to psi of X under the identification of first to map X to M as projection. Let's call it P. And then you map the P of X to um, so you map P of X under psi to an element of B, lift it to an element of A, and so then from uh, the universal property of a free module, you get a unique map from F to A, right? Let's call it. So if you call the psi compose P as P, let's call so, yeah. So maybe let's keep it as it is. So then let's call it this map as F, And then it's easy to see, like you can define a map from M to A by just taking any X, map it to M, and then, or maybe if you take any element of M, you can identify that element as an element of F because you have this inclusion map in the other direction. And then you can just apply F to it and you get what you need. So yeah, so that is our map from first U to I, and then you do A, you get a map from M to A, and obviously this diagram is commutative because of the universal property of the free model or the model map F. Or maybe I can call it as F tilde because yeah, F is the free model. Anyway, so we get 3 implies 2, and 2 and 1 are equivalent, we have seen, and 1 implies 4 and 4 implies 2. So that is about the 4 equivalent criteria. So from 3, what we can say is that any free module is, of course, projective, right? Because you can choose K to be the zero submodule. So from that logic, the first example is true, right? And also from that logic, you can say any finite abelian group, or in particular any cyclic group, Z mod n is never projective abelian or projective as Z mod. Right? It's very important to know one on which module, like on which ring we're talking about, because Z mod n is a projective module as Z mod n itself, because there is a free module. Right? So yeah. Now, for example, Q over Z is not projective as Z module. Again, because of the same logic, it cannot be embedded inside any free module because each element of Q mod Z uh, is of finite order. Yeah. Now, now some easy consequences is that, like if you have two projective modules, their direct sums will be again a projective module. That is easy because for one, if you have for like if you have two projective modules, say P1 and P2, you can embed P1 as a direct summand inside a free module F1, and similarly for P2, you get a free module F2. So if you just take the direct sum of F1 and F2, you get P1 direct sum P2 embeds inside as a direct summand of a free module, namely F1 direct sum F2. So direct sum of projective modules is significant. Now the main question is whether this is projective or not. Right? So there is a question to think. Anyway, so far we have only seen the free modules as the projective modules. Right? We have not seen anything which is not a free module but a projective module. So let's see. Or maybe is there any uh, projective module that is free or that is not free, I should say. And the answer is, like, it depends on which ring you are talking about. Like so this is so let's see the example first. So if you have say any say that if you have the ring as Z mod 2Z, direct sum Z mod 3. This is a ring. So Z mod 2 is projective as Z as an R module, right? Because it sits inside R module. So R module is projective, right? Or sorry, R module is free in fact because it's generated by one. So it's a free as R module, and Z mod 2, both Z mod 2 and Z mod 3 sits inside R as a direct summand. That is from the definition of R. So you get Z mod 2 is a projective R module, but it is not free because uh, that is again easy because if it were free, Z mod 2 would be like the cardinality of Z mod 2 is 2, and any free module over R will have cardinality power of 6. Right? So that is not true. Similarly for Z mod 3, so both Z mod 2 and Z mod 3 are not free uh, as R module, but they are project. Yeah. So now let's come back to the question about free module and projective. We have seen free implies projective, and from this example, we have seen not all projective modules are free. But when are both the notions same? That is true when suppose you have a PID. Say if R is a PID and uh, P is finitely generated projective module over R, then you can always embed P inside a free module of finite range, right? Because you can just take the generators of P and uh, embed P inside the free module generated by those generators of P. So in that case, you get a free module of finite rank F over a PID as a direct summand of this. And so this is a finitely generated uh, free module over a PID. So now basically the rest of the things follows from the structure theorem, because then you can identify P as a submodule of F, and you know any submodule of a finitely generated free module is free, so you get P is free. So basically any projective finitely generated projective module over a PID is free, and vice versa is always true. So free and projective coincides if P is finitely generated and the base ring is a PID. Yeah. So yeah, and in fact, something more is true. Like even if you remove this finitely generated condition, that again, then also this result is true, because any submodule of a free module over a PID is always free. That requires some Zorn's lemma kind of argument. So I'm not going to go into the details, but you can look up. You can find it on internet, I guess. Yeah. So these are some of the examples. So now let's see the analogous version of a projective module. The converse thing is inject. Yeah. And so, and if you look at in a more abstract way, so in any category C, if you have category C, uh, you can define what is a projective object. That is again easy, because suppose you have AP from A to B. Let's take it as AP. So if you have an AP from A to B and given any arrow from M to B, say phi, if there exists an arrow from M to A psi, such that if you take phi and then compose it with F, you get this. So then this implies a misprojective object. There is any that more abstract way. So if you look at the diagram, then you can say you have this AP, you have this phi, you can lift it up to psi. So this is a projective. Now, if you reverse everything, so and maybe we are talking about say in any abelian category, then you have the notion of zero object, so things becomes easier. So now, if you like take the dual of that notion, so then if from say if you take dual means you are just reversing all the arrows, so you get say you have this. So here if becomes a mono, right? So given any mono from B to A and any map from say you have B to A, let's call it phi. If there exists a map from A to M such that this diagram is commutative, then we call it M is injective object. And in R module category, this is same as saying in R mod category, the category which we are interested in. So in that case, you can say So given any injective map from A to B, or say B to A, you have this functor, right? Home dash comma M, which is a contravariant functor. So this goes from home AM to home BM, right? So this is surjective, means, or this functor is exact, means it is right exact, because any home functor is always left exact as well. So this is right exact, means given any monofrom, or given an injective map from B to A and any phi from B to M, you can lift it up to say psi, such that you get if compose psi is phi. So yeah, that is injective module. Now let's look at some of the examples of an injective module. Or maybe I should talk about them in the next video, because it's not very easy to find injective models in general. Yeah. So for that we need the well-known Bayes criteria. Bayes criteria. And so basically it says that or say if you have a module, say M over R is injective if and only if any map from any ideal I to M has an extension from R to M, where this is ideal. And so from there it will follow that over a PID, any injective is same as any divisible R naught. And from this criteria it's easy to see that Q over Z is so Q as Z module is injective, then Q over Z as Z module is injective, or Z power R as Z module is not injective, right? Because it's not divisible. So yeah, these are some of the examples. So here we have seen that this is a projective module as Z module, but it's not injective. So there are projective modules, or there are injective modules which are not projective. For example, so far we have not seen, but you can maybe show that Q is not projective as Z module. So that would show that there are really no connection, like there are not easy implications from whether a projective module is injective or vice versa. So here it is not injective, but it is projective, and here it is not projective, but it is injective. Yeah. Now, so the main thing is what you can show is any R module M can be embedded inside an injective R module. So that is an interesting observation. So we will see this one, proof of this one, and also the proof of this result. I will not prove Bayes criteria because that again requires some Zorn-Lemma kind of diagram. But once we assume Bayes criteria, there is the rest of the things are easy to show. Yeah. So, and this is true for a PID, remember. If the base ring is not a PID, then this is not. So, but again, one you will see, you can easily see that one side of the implication is true in over any integral domain. Yeah, so maybe you can think of that, and maybe I will close the video. So.